workshop atelier sécurité incendie va reprendre. Et j'ai le plaisir de vous présenter donc Christian Dagenais, qui est aussi notre partenaire dans cet événement. Vous savez bien que c'est un partenariat FCBA, BRI et FPInnovations.
So today we're speaking about fire resistance, which is a really defined and precise concept. However, we need to understand what is fire resistance first. For those fire experts in the room, nothing new for you, unfortunately. However, fire resistance is commonly used widely to mention about different behavior. Whether we say it's a fire-resistant material in terms of flammability or ignition or different things. So this has to be cleared out and kept in mind that we're speaking about really one simple concept. And then we'll go through on how to assign fire resistance to mass timber elements. I'm going to show you as well some results from Canadian fire tests that we conducted over the years. Some guidance on connections. Unfortunately, connections are still today one area that is missing some guidance on how to design for fire resistance. There are plenty of research for, I would say, short duration of time, so up to 45 minutes to 60 minutes in some case, but otherwise 90 minutes and 2 hours, there is very no test data available for now. So what is fire resistance? Essentially, as I say, it's a concept that allows for providing fire compartments within a building by providing fire barriers that exhibit the required fire resistance under specified conditions. So there's many things, many defined terms that all interrelated into that whole concept. So fire resistance is essentially just the ability of a material or an assembly to resist some criteria for a given period of time. What we're trying to achieve, or that concept is basically aimed at getting into the design within that phase here. We had a previous talk on how to reduce the ignition or flammability of the product. Then that goes with the reaction to fire in terms of the European classification. In North America, it would be the flame spread rating that we evaluate differently. Otherwise, in a standard development, you have the flashover that occurs at some point, and then that's where the structural fire resistance comes in. So there's many aspects to it. Basically, fire resistance is, of course, the load-bearing elements, so posts and beams, walls. But it is also used to prevent fire from spreading beyond the compartments, so it has to be kept confined within the compartments. It could be the walls, the floors, but also the windows, so the glazing, could be the fire doors, different assemblies that needs to maintain a fire from going outside. And there's also some effect from fire from spreading to neighboring buildings. So there are essentially 3 criteria, and I apologize, Koji did already showed similar slides, but fire resistance, there's 3 criteria essentially that it needs to meet. So you have the load-bearing capacity. It has to be able to withstand the applied load for whatever duration. In the case of tall buildings, it would be something between 90 minutes and 2 hours. You have also the fire integrity, so it has to limit the passage of flames and smoke through the assembly. So that can be any compartment boundary. So it could be walls or floors, or again, it could be doors. And then the last criteria is thermal insulation. So you have to limit heat transfer from being too excessive on the other side, so that if you have any easy to ignite combustible material, then it would ignite, and then you're basically allowing a fire from spreading from one side to the other, but without having actually flames going through the assembly. So not all materials need to fulfill the same criteria. Obviously, a column or a beam cannot limit a fire from spreading from a compartment, so it only has to fulfill the load-bearing criteria. And these are well defined in all the standard test method anyway. So you have basically different tests. Typically, we assess fire resistance of an element through a standard test method. There's the ISO test method. In North America, I have the ULC or the ASTM, depending Canada or US. And in terms of fire severity, it's very all similar. So you have a really rapidly increasing fire in the early stage, and then it kept on going and going, as opposed to like for example, the Japanese fireproof test that is up to 1 hour, and then you go to the cooling phase. It is a test that is really costly. It's essentially a one-shot deal. So once the fire test is started, you cannot just stop to adjust something. And typically the results is applicable to what you just tested. Hopefully, luckily, I would say we have calculation methods. Pretty much all countries now have analytical methods to calculate fire resistance. There's many similarities in terms of concept with the reduced cross-section method, strength adjustment factors, charring rates as well, depending on the product. So they're all pretty much all the same and all validated methods. Actually, I would say it's one of the most important things is that any method should actually be validated from full-scale tests. And this has been done throughout many years in both Europe, US, Canada, and different other countries. Some example of fire test results here. These are essentially US test data that we tried to replicate through the Canadian calculation method. So we have some timber and glulam beam in bending. And you see the straight line here, maybe not that obvious on the screen, but the straight line is basically if the test method would be exactly the same as the test. So we see that it's still conservative because we predict a lower fire resistance. When subjected to tension, it's more accurate. And then if you have columns, you have a greater variability because of the end fixicity, but otherwise you see that the calculation method usually predicts well and slightly underneath what you would actually have through a test. There's also other test results on structural composite lumber and CLT floor and walls. And most importantly, what I'd like to highlight, especially on the CLT, is all the test results that are beyond 90 minutes. There are many test results available, not just Canada, but there's plenty of other tests that shows that 90 minutes and 2 hours can easily be achieved by fire resistance. What I'd like to show here is a summary of the CLT test that we conducted in Canada. So there's 20 tests that I'm showing here. There's different configuration, different thickness of laminations in the panel, different stress grade of CLT, and different loading levels, as well as whether sometimes the CLT is protected by gypsum board or not. In 20 of these tests, there's only 4 that actually is not beyond the 90-minute marks. And we also have, for example, floors that were loaded at 100% of their capacity, and we reached 178 minutes. So it's a 3 hour, essentially, technically not a 3-hour test, but for 2 minutes for this stock here, it's a 3-hour fire resistance. So really, to fulfill the needs for higher, taller buildings that needs greater fire resistance, it can easily be achieved, although it's wood. We also tested timber concrete composite. There were some talk this morning in the main stage that there's a need also for longer spans, composite with timber, for improving vibration, acoustic. So we tested 3 assemblies, and they easily reach beyond 3.5 hours of fire resistance. We tested the nail laminated timber, so just 2x6, 38 by 180 something millimeters, nailed together with single truss plates here, metal light gauge steel truss plate that were embedded in it, and we just poured the concrete. We also tested a CLT element, a 5-ply CLT that we used 45 degrees screws, self-tapping screws, to use as shear connector. And the last one that I'm not showing there, but it was essentially just LVL beams on flat that we drilled bolts in it, like screws, I would say, and we just poured the concrete on top of it. And they performed really, really well, well beyond what would be required to do for doing a tall mass timber building. So going back on how is wood capable to achieve such performance, is we have to understand what's going on once it burns. So wood is combustible, so it will ignite at some point if the conditions are there. But after 300 degrees is taken usually as the char front line, where there is no longer strength and stiffness and any capacity. And you see that there's a really steep temperature gradient going inside the wood. So above 30 to 35 millimeters, essentially you're going back to full strength. So you have 100% ratio of your initial capacity. So wood is a natural product. So when it's exposed to some sort of threat, it reacts, so it chars, and then it protects itself underneath from fire. The concept of the reduced cross-section is not, as I said, is not necessarily new for those who do the structural analysis on a daily basis. So we have an initial cross-section, a depth, and a width of an element, and then we can determine what is the charred layer. So it's a commonly used for most softwood products. It would be 0.65 millimeter per minute or 0.7. It could be different if you have a product that is different. So if you have some test data to prove that you could use something else, you could technically use it. So the charring rate times 90 minutes or 120 minutes will give you what you will lose after a given period. And then we add a heated wood that is an additional 7 minutes. That is just, we're kind of ignoring that extra layer. The thermal effects has started to decrease the mechanical properties of the wood, so we just remove it as well. So it's kind of an additional layer of safety that we put into the structural calculations. And then, well, you use what's left with traditional structural behavior equations, and then you can calculate what's the residual resistance of your element. So whether it's a beam or a column, then you have different things to look at. For the structural engineer, one important thing to understand is that there's also significant differences between normal design and fire design. So usually the ultimate limit states would be more critical in fire. So it will be the strength that will govern. If typically in wood, floor vibration or floor deflection might govern as opposed to strength. Sealed walls might be governed by strength, and then in fire they might also be governed by their capacity. Some of the elements, if you combine steel, concrete, wood, you may end up with some internal stress that you didn't really encounter for when you do your normal design. So in thermal design, you should, for fire design, you should need to consider them as well. You may have some strength and stiffness reduction obviously because of the heat. Your cross-section changes, so it could be the charring of the, obviously charring of the timber element, but spalling is also a common phenomenon that we need to account for concrete. You have different safety factors as well, so the probability of occurrence is not the same in terms of fire load case. And you may also end up with different failure modes. So that also needs to be checked, and especially for connections. So 3 things: if you have a element subject to tension force, you do the steps that I just showed you previously, and so it's a reduced cross section, and then you evaluate what's the stress the applied from the force, and whether if your residual section is still capable of taking it. Compression elements, so columns, is a bit more sophisticated. You have to make sure to check that the second order effects will not become an issue. Because as the column will char on the sides, then you have the neutral axis of that column will change, because the load is still applied at the same place on top, but you have the neutral axis of the column that is changing as over time. So you have to basically go and do some iterations to make sure that you do check buckling or the P delta effects for columns. Beams, same thing. If you have a simple span beam, it's essentially the same thing to check. Maximum bending moment will be at mid-span. But if you have a continuous span, then it might be more tricky, and you'll have to double check at different places, the same as if you would do basically for normal design. Also, special consideration, when we do a structural analysis of a bending member, we presume typically that the top element subjected to compression is restrained. So you have a decking on top, there's nailing, or you have secondary beams at whatever spacing that restrain the top flange from buckling. So in fire design, you have to make sure also that those elements remains there for the required period of time. Otherwise, you need to recheck the slenderness of the beam every time to make sure that it's still good. Integrity. In Brad's talk, he did mention how to the importance of sealing the joints in between the elements. So this was one of the compartment tests done at Carleton University that the students forgot about putting caulking in the between the CLT panels. So we ended up with flames occurring through the assembly very rapidly. So it's really important if you want to fulfill that integrity criteria that every joints are really properly sealed. Same with the surface penetration. So we did some amount of fire testing as well. So we use fire stops device that are already approved for concrete assembly, and we use that in the CLT. What we found is to make sure that these, if you have a metallic duct that goes into the assembly, that it's not touching the wood. So you have to put some insulation around it, and then you put the seal on top. So if when in the event of a fire, if that pipe here heats, it will not accelerate or induce charring on the side of the element. So you have to protect all of these and think a little bit differently. But overall, all devices that we tested for concrete really work well. Thermal insulation. Wood has a really low thermal conductivity value. So from the graph I've showed previously, essentially to meet the 180-degree rise criteria, we only need basically around 7 millimeter of wood if you have a fire on the other side. So it's really efficient. These are the results that we got from our first round of CLT testing. And in that column here, we have what was left of the assembly at the end of the test. Here is the temperature of the furnace, and this is the temperature rise that we got during the test. So really, you end up with over 1,000 degrees Celsius, and you have about 5 to 10 degrees Celsius rise on the other side with 10 centimeter of wood. So it's really, wood, in terms of insulation, wood is really efficient, but we have to make sure that the assemblies are also fulfilling the integrity. Obviously, we're in the context of tall wood buildings. This one of the full-scale tests that we conducted in support of the 13-story building in Quebec City. We went from component basis to the full system basis. So we tested the wall assemblies and the ceiling assembly in the furnace test, the standard fire resistance test. And obviously it was new, it's 13-story, we're way beyond what the code prescriptive code is permitting. So there were some stakeholders that wanted to see the actual performance, although it has been tested through furnace tests. So Quebec government did allow the funding to do the tests, which we did at National Research Council in Ottawa. And the test really performed well. So it was similar to what Brad presented with the in the US. We kind of replicated a one-suite apartment with furnitures and wood cribs to increase the fuel load. There were also here it was a 40-minute door that was kind of simulating the door to external corridor, and this was a 3-story high CLT vertical shaft. The firefighters back home was really against that that option, so they were afraid that basically that fire would go through. So we instrumented from the inside all the shaft, and really there were no smoke, no temperature rise at all, even after 2 hours of a real fire occurring in that compartment. Last point, connections. I don't have much to say on connections because we know that there's still some gaps to learn on how to design connections for fire design, especially for 90 minutes and 120 minutes. But they also do require special considerations. We can evaluate a beam for 2 hours, we can evaluate the column for 2 hours, but if the connection between them is 15 minutes, it doesn't give us much. So connections are complex. Those who, the structural engineers who do connection design knows that it is not the easiest part in a concept. We have a wide variety of fasteners, whether it's screws, bolts, dowels, drift pins, whatever. We have different configuration as well: exposed steel plates, internal seat plates, hangers. So there's many factors that need to be think of, and there's a lot of testing still going on, and we'll have some more hopefully in the soon future. But the main guideline that I would recommend so far from all the tests that has been done is if your fasteners are located within the reduced cross section, so after you calculated what would be the reduced section, if all your steel elements are in there, you can assume that your connection it has achieved the rating that you're seeking. So here is just well, this is the result from one of the tests. You can see that the steel plate was right here, and you had some bolts going through. And this is the simulation of the using finite element, and you can see that the bolt is inducing some heat through the assembly. So that's why in that case the bolt was outside, but if the bolts were located inside, so in case protected for the required period, we would most likely not have seen this effect inside. So as I say, if your fasteners are located inside the reduced cross section, basically you still have a good and valid connection. So in conclusion, there's a lot of testing that has been done out there. Calculation methods exist for a number of years already. Eurocode 5 is really well detailed. There's many other standards, Japan, Canada, US, that provides how to calculate fire resistance, but they sometimes have limitations on the duration. However, test shows that beyond 2 hours, it can easily be achieved by mass timber elements. So it's really not an issue. It's a matter of doing the calculations, but it's a little bit more complicated because you have a lot of other things to think of, at least from a structural point. Well, I just summarized those 3 points. So lastly, acknowledgements. So, thank you.